Hello everyone and welcome to our fourth lesson. Today we'll start to talk about binary numbers. So who remembers what we did during our last lesson? That's correct, very well. Yesterday we created our own number systems using circles and squares. So who can tell us what we can communicate using only those two symbols? They could be squares, circles, stars, apples, anything. Is there a limit? So I'd like you to answer that question on Google Classroom and then share with the class. Someone mentioned that we can communicate answers to a yes or no question. That is correct. I also saw flipping on an on-off switch and turning a device on and off. All of these are great examples. What we've been describing through these examples is a binary number system, a numbering system that represents numeric values using two unique digits, zeros and one. That is what we'll learn more about today. As we saw in our last class, if we only had one place value and two shapes, there is only two possible patterns we can get, either a circle or a square. What if we have two place values? In that case, we can make two sets of the previous patterns. Then insert circles in front of the first set and squares in front of the second set. This makes four possible patterns. What about three place values? Well, we can make two copies of the two place values. Then, just like we did before, fill in the first set with circles and then the second one with squares in the front. This makes up how many arrangements? 8, 9? 8 is correct. Let's make it even more complicated. Instead of two shapes, what if we had 10 shapes? As you have noticed, I started using numbers 0 through 9 instead of shapes. We could have used geometric shapes or we could have used letters, but the resulting number of patterns would end up being the same. Since we as a society have collectively decided to use numbers 0 through 9 as a number system, we're more used to recognizing patterns that involve these familiar shapes. With two place values, we can make how many unique two-shape patterns? 100? Exactly 100. These are the numbers 00 through 99. But what happens when we count up to the last shape? A really quick quiz. What comes after the number 99? Everyone take 1 minute to think about it and raise your hand on Zoom if you think you know. Also complete this question on Google Classroom and submit. A 100 is correct. As we've learned in algebra class, when we run up to the last shape, which is 9, we roll over back to 0 and add 1 in the next place to the left. This is the place value that we have used all our lives. So where is this heading? The binary number system is a number system with two shapes. Instead of shapes, we use zeros and ones. In this example, each pattern maps to a decimal number from 0 to 7. Is there any questions about anything we have talked so far? If there are no questions, we'll jump into today's activity. Today we'll be using Flippy-Doos. These templates will be on your desk if you're in school, and in the Lesson 1.4 folder in Google Classroom if you're in your own houses. Flippy-Do is a tool that will allow you to quickly and easily translate between the decimal number system we are used to as humans and the binary number system that computers use. The first row of the Flippy-Do shows our base 2 raised to the power of 0, 1, 2, and so on until 7, starting from the right going left. The second row numbers are the results of the exponential expressions above. As we convert the numbers, we drag and drop the zeros and ones into the third row of the online version, or cut them out using scissors on the paper template. Each place value represents 1 bit, which is short for binary digit. A binary digit can be a 0 or a 1. Your Flippy-Do has 8 bits. Together, 8 place values or bits make up 1 byte. Since computers represent information digitally, the lowest level components of information are bits. Now let's move on to an activity to see if we all know how to use our Flippy-Doos. Try these problems out and don't hesitate to use your templates. We'll try them out by ourselves first and then we can do them together. Actually, I'll do the first example. To convert the decimal number 7, I would flip up a 1 in the fourth position because 4 can fit into 7 ones. The next bit to the left is 8, which is too big. Then I have 3 left. I flip up a 1 into the 2's position and still have a 1 left over. Finally, I flip up a 1 into the 1 position. There is no remaining number, so the binary number that represents the decimal number 7 is 111. For the next 10 minutes, we'll continue to practice with our 2 number bases, decimal and binary. After you finish each of the 4 parts of the activity guide, I want you to check your work with your partner. Feel free to use your Flippy-Doos as you work through the problems. Now let's wrap up. It's important to know the difference between binary and decimal number systems. As a review, the decimal number system is a base 10. There are 10 different symbols used to represent decimal numbers, 0 through 9. The binary system is base 2. The 2 different symbols used to represent binary numbers are 0 and 1. Today, we used our Flippy-Do to convert between binary and decimal number systems. While it is easier for humans to use the decimal number systems in our everyday lives, we will see later in this unit how electrical signals inside computers can be best represented by using the binary number system. Now that we've had a chance to practice, let's find out what we've learned and what we still have questions about. Write down 3 things you learned today, 2 things you found interesting, and 1 question you still have. As a homework, please work through exercise 8.2.5 on CodeHS. It's a game that gives you practice on how to convert binary numbers to decimal and decimal numbers to binary. Try to gain a minimum of 500 points and then hit submit. Also, in this last few minutes, add to your journal the vocabulary definitions of bit and byte. See you tomorrow.